Hello, everyone. Hopefully you're having a great week so far. Before we get into the lab, there's a few logistical things I want to cover about the lab midterm. So obviously grades are out, and depending on when you're watching this video, they've probably been out for a while. But I sent an email earlier this week with some sort of tips in case you didn't get exactly the grade you wanted on the midterm on what to do going forward to get hopefully a better grade on the lab final. I'm not going to go over those in the full depth now, but I'm just going to very briefly touch on the 3 points I talked about. One, you'll need to be completing all the labs in their entirety. This includes discussion questions, includes connecting these ideas to lecture. Just taking the quiz and getting 10 points on it doesn't necessarily mean you're getting everything out of the lab that you're meant to get out of it. And that leads into number 2. If you have any questions at any point on any of the lab materials, please reach out to me. My job as a TA is to help you all as best I can. But if you're not asking me questions, I can't know what I'm teaching well and what I'm not teaching well, and what would be helpful to have more information on. So if you ever have any questions, please shoot me an email, drop by my Zoom office hours. I am here for you all. And then third, I caution the over-reliance on Google on especially our labs materials. So you might, when you're Googling questions in the labs, you will find information on most things probably. And sometimes that information is right, sometimes it's wrong, but a lot of times, even if it's right, it's not necessarily pertinent to the question being asked. So everything that you need to know for this lab can be found in the lab materials, in what's given to you. And for the labs section in general, that's true. So I caution the use of Google too much. Obviously, it's a great resource, but you don't want to end up putting something wrong or end up answering a question that wasn't asked. So that's sort of all I'm going to cover on the lab midterm. If you have any questions, of course, please reach out to me. And now let's hop over into the lab, which hopefully will be a good one. So this week's lab is lab 8, Fluvial processes and landforms. And so we're actually going to be taking a look at some of the rivers and streams around Columbia. So this will be sort of a localized lab in a way, and hopefully you all will find it interesting. And maybe it'll even inspire you to get out there and go check out some of these rivers. Obviously, the river walk in Columbia is beautiful. And if you haven't been yet, about 30 minutes south of Columbia is Congaree National Park, and it is absolutely gorgeous. So I definitely recommend making a trip out there at some point. And now's actually a great time to go, probably, because during the summer and the hot months, the mosquitoes are just terrible at times. So let's get into it. Sorry about that. There we go. So first, covering the big topic of drainage networks. Drainage density is the total channel length over the drainage area. And usually a higher drainage density means more channels per unit of area. And second, drainage patterns are the geometric shape of a drainage network. You see 6 common ones over here. And it would be useful to have a general idea of what these 6 look like just going forward, and how to identify them. But they're pretty distinct on their own. So next, let's talk about stream order. So 3 definitions you might need to know. Stream reach is a segment of a stream or river with selected beginning and ending points. So if we're looking over here at this image on the right, this might be the beginning point and this might be the ending point. And so then this number 1 would represent a stream reach. Stream order is a way of classifying streams relative to their location within the larger river system. And we'll go over how to calculate and classify stream order in just a second. And then a first order stream, which is anything in this picture with a 1 next to it. These are the uppermost reaches of a stream channel, and they have continuous flow in parts of their beds year-round during normal rainfall years. And so that's sort of the cutoff point between a first order stream and maybe something that's flowing into it, is that continuous flow. Now let's take a look at this image and figure out how to calculate stream order. So, and the lab materials also go into this. So if this explanation doesn't make sense, hopefully that one will. So essentially, your first thing you're going to look at on the outermost part, what we are just talking about, uppermost reach, is a first order stream. So you can label pretty much any start as a 1. And you can see that they are around here, regardless of sort of where they're starting relative to the channel as a whole. So then when 2 1s come together, they make a 2. And so you can see that here, 2 1s make a 2. 2 1s make a 2. And when 2 2s come together, they make a 3. And you see that here. But, and this is really important, smaller stream orders coming together with larger ones stay at the larger stream order number. So you can see here, 2 2s make a 3, but when a 3 and a 2 comes together, it stays a 3. And you can see that example sort of right here in the middle. And when this 3 comes together with this 1, it stays a 3. So that's sort of the important thing to look out for when you're calculating stream order. Only the largest number is going to matter. So if 2 of the same size come together, they go up 1. Or if a larger one and a smaller one comes together, it's the larger one. Those are sort of the 2 main ideas of stream order. If you have any questions, reach out or take a look at the lab, and hopefully it'll have a little bit of a different explanation that might make more sense. But this is a really important concept. So make sure you understand how to do stream order. And there'll be some questions about that during the lab. Now let's get into a little bit more of the background content again. We're going to be talking about sort of fluvial landforms in general. And so first, alluvial channels are going to be our focus. These are channels with non-bedrock bottoms. So they have bottoms that can sort of move around, loose, those sorts of things. And there are 3 main types of alluvial channels. So there's the braided channel, which you see here, and which we talked about last week in lab a little bit. And so braided channels are numerous branching and rejoining channels separated by bars and islands. And we'll be talking a little bit more about what those might mean in a second. But you can see that image here. They sort of break apart, they come together. That's a braided channel. Then you have meandering channel, which is a single channel with bends in it. And these bends reduce the channel gradient or steepness. And so you can see that up here with this image in the top right. That would be an example of a meandering channel. And then finally, there's the straight channel, which you see in the bottom picture. These are usually the result of human activity. There aren't very many natural straight channels, and they're not particularly important for this lab. So now we're going to go over the fluvial landform features. I'm not sure if you all have covered this in lecture or not, but I thought it would be helpful. If not, they are covered in the lab, but there are no sort of images provided with them. So I wanted to try and get an image of each of these different landform features so that if the text explanation doesn't make sense, hopefully the picture does. And I'll move the little video thing out of the way so that you can see it. So this top image is an image of a floodplain. And so that is a flat area next to a streamer channel that is flooded relatively frequently. So you can imagine in that picture that if you had a big rainfall come in, a lot of that area around would become flooded. And then these 2 very important cut banks and point bars. You can see in the bottom here. So a cut bank is a concave channel bank formed on the outside of a bend of a meander by erosive flow. So you can see how this channel is sort of eroding away here and making that cut bank. And then a point bar is a low curved ridge formed by deposition along the inner bank of a meander. And so sort of opposite this cut bank, you see a point bar here where this sort of sand probably is being deposited and forming that point bar. So those are important. Make sure to know the cut bank and point bar and their differences. So next, we have oxbow lakes, channel scars, and scroll bars. Sorry about the order of these images on these PowerPoint slides, but I tried to label them next to each one in case it's a little bit confusing. So first, Oxbow Lakes. They are a former meander bend abandoned when cut off by erosion and channel migration. So in this image here, you can see how maybe at one time the river would have meandered around here and connected back, but that is no longer the case. It's been cut off. And so what's left here is the Oxbow Lake. Then up here in the top right, you can see a channel scar or many channel scars. So a channel scar is a former channel segment abandoned and filled with sediment. And you can see here that there appear to be a few places where the sort of river is still running through, maybe through here as well, but there are tons of channel scars all over the landscape. So that's up here, a little bit down here it looks like. You can see these places where the river no longer connects, the channel isn't connecting anymore, and it's sort of filled with sediment instead. And then last, in the top left here, we have the scroll bar. A scroll bar is a low arcuate ridge on the inside bends of a point bar. So you can see, or maybe more imagine, that there might be a point bar around here, or maybe there's one right here. But you can see how, if you were imagining this point bar forming over time, you can see where these sort of scroll bars have formed that are ridges of the old point bars. So you can imagine those here. And that's sort of what a scroll bar looks like. And then finally, we have the last three natural levees, back swamps, and Yazoo rivers. I wasn't able to find a good natural example of these, so I got this diagram that sort of shows all three. But a natural levee is a low, often subtle ridge near the channel where overbank deposition has left deposits of relatively coarse sediment. And you can see that here along the banks of this channel, there are these two natural levees. And then a back swamp is a low swampy area between a natural levee and the valley wall, which here this represents the valley wall, and this sort of area represents a back swamp. And you can imagine that it would sort of fill with water and be relatively swampy at times. And then last, the Yazoo River, which you see sort of come in here, called a Yazoo stream here. This is a tributary stream that flows parallel to the main channel, which you see here. So this is the part where it's flowing parallel down the back swamp area of the main valley. So sort of this area in here. So it's prevented from joining the channel by that natural levee. And you can sort of see that here as well. All right, so those are our big sort of fluvial landforms to be thinking about as you do the lab. Hopefully those images have helped clear things up if there was any confusion. And again, if you already went over this in lecture, I apologize. In terms of other things we need to know regarding floodplain features, dynamic equilibrium is the changing of landform features while maintaining a constant average shape, size, and balance in forces through time. So you can imagine as these rivers move, things are going to change, but sort of in dynamic equilibrium, the averages of these things sort of stay consistent, even if the physical aspects change over time. We'll be looking at all of these things, or many of them, on local bodies of water around Columbia, South Carolina during the lab, which I'll get into a little bit later. And then the second sort of major topic we want to talk about is the fall line. So the fall line marks the transition from the Piedmont to the Atlantic coastal plain up the East Coast. You can see a map of that here. And it is sort of the boundary between the Piedmont's harder metamorphosed rocks and the coastal plain's softer sandy deposits and sedimentary rocks. And if you're thinking about Columbia and if you've been out to the river, then you can even see the effects of this fall line by the rocks in the river, which you can also see in this picture if you haven't been out there. And so these rocks and shoals are sort of the final edge of those harder Piedmont rocks. And that leads well into thinking about why are there cities along the fall line in general, and what sort of effects does the fall line have? So a lot of cities along the East Coast have formed along this fall line. And that's in part because of easy river transportation to seaports, and also in part because of available water power for mills and factories. And you can see that in Columbia. Maybe even some of you live in some of these old mills. Olympia, Granby, those used to be mill buildings. And so they would have been on this river for this reason. However, the fall line is generally sort of the head of navigation on the rivers, and that's due to the presence of rapids and waterfalls. And so you can imagine with the rocks too, where Columbia is regarding the river, because of that presence of rocks, it becomes very difficult for ships to navigate further upriver. And so Columbia is sort of a natural stopping point there because of that. And because of those sorts of rocks and rapids and waterfalls, many cities later constructed canals with locks to bypass these dangers. And you can see in the background here, and maybe you've been down there before, to the Columbia River Walk, the Columbia Canal, which was created to bypass those dangers. Sorry if you can hear it, but my dog is barking a little bit in the background. Ollie. Okay. Okay, so back to the fall line. Over the course of this lab, we will be examining 3 river reaches that flow through Columbia in order to take a look at the transition from the Piedmont to the coastal plains here. And to do that a little bit, we'll be using some calculations explained over the course of the lab. Most of these calculations you are already familiar with. So sort of river distance, straight line distance. You might not directly work with them yet, but we've done similar things in Google Earth Pro before with sort of path and straight line distances. Slope, we've looked at before in Google Earth as well, and elevation. Although some of those values will be provided for you because of sort of confusions about where elevation might be and issues with Google Earth Pro. But we have not talked about yet sinuosity, which is a measure of how straight or curvy a channel reaches. And this is calculated by the river distance divided by the straight line distance of a river. And so a perfectly straight river would have a value of 1. And so if you're thinking about this, the river distance is sort of a path distance that would follow along the curves of a river, and the straight line distance would just be point A to point B directly. And so you can imagine how a straight line would then, those distances would be the same with a value of 1, whereas a curvier river might have a much higher value. All right, so that's the content we need to cover. I'm going to quickly hop over into Google Earth Pro. 1 second, it is not showing up. Here, I'll hop over to the desktop. All right, so now we are in Google Earth Pro. And so let's think about this for a second. Most of these things that we're going to be talking about, you've covered in the lab already. So I'm not going to go back over those. Searching for coordinates, taking distances, those sorts of things. I am very briefly going to show you again in case you've forgotten. So when we're talking about river distance, you're going to want to come here, or straight line distance even too. So straight line distance, you can sort of click 2 points like this. So if you want the straight line distance of this area, it might look something like this. And then with river distance, you can do path, and then you can sort of click along like this. And you can get an idea of just how much longer that river distance might be. But this is a helpful tip in case you haven't come across it. Let's say I misclicked and have something like that. I can right click, or on Mac, sort of that double click, and that will get rid of the most recent point. That way, if you make a mistake, you can sort of go over it, fix it without having to completely start over. And so those are those tools. And then the other tool we're going to be doing is looking at changes in the river over time. So the way you do that is you come up here and you click this little clock. And with this, you can drag it to the different images Google Earth has. And so if we just scroll through these quickly, and you'll be doing some other work with this, but you can see how this sort of river has changed over time. This isn't necessarily a section with the big changes, but if you look up here, you can see this point bar, and then it goes away. And so you all would be sort of thinking about what are the implications of these sorts of things and looking at some interesting examples of them in the Columbia area over the course of the lab. So that's everything with Google Earth Pro. Let's hop back over and just take a very brief look at the lab. So here is the background information, some of which we went over. Make sure to read over it again and make sure everything makes sense. And if it doesn't, ask me any questions. Sort of these features here, you can see they give the same description I did, but they don't have any pictures. So hopefully those pictures might have been helpful. Some more description of these sorts of features, and then we get into the lab. So the first lab is a sort of semi-theoretical quantification. So you'll be looking at the Gills Creek watershed around Columbia, and you'll be doing some of those calculations like drainage density, stream order, those sorts of things, and thinking about what those mean and connecting them to some of the ideas you've talked about in lecture. And then second, we'll be going into Google Earth Pro, like we just did, and using some of those tools. Here it shows you how to look at historical images. And you'll be investigating some different features around Google Earth Pro and describing them. So some of those features that we talked about already, you'll be seeing in the real world in Google Earth Pro. And then finally, there's sort of a fall line activity like we just went over. Make sure to read through this background information, but some of it is what we already covered. And so you're going to have these 4 place marks with the elevations given. And you're going to do these calculations for the areas between those 4 place marks. Then you're going to think about sort of what these mean and look at some objects around to answer the rest of the questions. As always, there will be a quiz on Blackboard due this coming Sunday by 11:59 p.m. So hopefully that is, hopefully that goes well. Hopefully you all have a great week. As always, my Zoom office hours will be the same. And if you have any questions, please reach out to me. All right. Have a great week, everybody. Thank you.